What I'm going to talk about today is a project that I got the opportunity to be, if you will, the chair of this year, and that's North Plains EPIC. Okay. Before I get into it too much, I want to make sure I give credit where credit's due. This is a project that took quite a bit of funding to make happen and quite a bit of planning beforehand. The primary funding source for this is one that I feel like we've got a very great working relationship with, and it's been worth all of the effort that's been put in to get this relationship, and that's the North Plains Groundwater Conservation District. I think there's a lot of progress being made up there towards being very good stewards of that water resource, as well as keeping in mind that there's livelihoods and production that needs to be maintained in that process. I'm glad to be working with them on this. Obviously, this is a project that was heavily geared up by Texas AgriLife Extension Service. It was one that dealt with myself as a specialist and 6 county agents, and then a lot of the ancillary funding and some of the educational venues that were offshoots of this were funded by Ogallala Aquifer Program, Ogallala Aquifer project funds that I had secured for educational delivery. And so I'm grateful to those entities for letting this project go forward. As we get into this, the basics of this project is that where the acronym comes from, Efficient, Profitable Irrigation in Corn, EPIC. Okay, pretty simple, pretty trendy name, I think. I don't know exactly how we came up with it, but I'm glad this is the one we chose. The premise of this is just like what Rick was mentioning. There is a tapering off point when you have a corn crop in relation to the water applied. So we look at this chart. On this left axis here, it represents the production of corn in bushels, and it's representing this blue line. Okay, and this is a crop that's indicative of the 2011 crop year, where there is, we estimate, about 20% automatic stress loss from the environment in terms of yield. Okay, this right line here, or this right side, represents the net residual returns per acre, or in simpler words, the profit per acre of the crop. And this all corresponds to this amount of total seasonal water applied, which is represented on the x-axis. That being a culmination of irrigation, soil storage, and precipitation in season. Okay, what you see is that you've got on this curve a line that's progressively increasing, meaning your yield is increasing with each incremental bit of water, but this line is kind of flattening out as you go until you reach an inflection point. Ultimately, it flattens out and then it starts to come off of the other side, indicating that, like all crops have, they've got a physiological limit to what kind of yield they can give per inch of water applied. In economic terms, this would be the law of diminishing returns, where each inch added is going to yield you less inch than the previous inch did. Okay, so this is something to understand in terms of managing your yield and crop, but it really becomes very, very important when you combine that now with a crop budget. Okay, and as you go through a crop budget and combine this and get this to the best common denominator we know in any business of dollars, what you find is that you can relate this to profit per acre. Okay, so if you look at these with the same x-axis, take a good look at the shape of these lines. As the yield is increasing, at the same time, your profit is potentially decreasing. Okay, so what does that mean? It means there's a peak point on your profit line which should be using less water than what your peak yield would be using. Okay, so as a strategy, what we wanted to look at is if you start to manage for that maximum profitability rather than that concept of maximum yield, would it be able to, 1, conserve water, and 2, potentially improve the economics of the farming practice? So in this scenario, if you look at it, you've got a maximum physiological yield around 34 inches of total water, okay, combination of those 3 sources, and then a maximum economic return that occurs at 29 inches of total water. Okay, so in theory, in this year, what we would find is you could potentially save 5 inches of water and at the same time boost your bottom line by a noticeable amount. Okay? So this is what we looked at exactly in 2011 pre-plant. We looked at a curve that was based off of $7 grain, $5.50 per MCF for natural gas. Come across a maximum profit point occurring at 30 total inches of applied water, not applied but total water. Okay? Under this circumstance, you'd come up with a maximum yield at 254 bushels per acre using 22 inches of irrigation and a maximum profit with a corresponding subtraction irrigation down to 20 inches of irrigation. This was going into the year, obviously, hypothetical based on averages. You get into the year, and obviously our conditions changed a little bit, and so this scale starts to change quite a bit. So now we're looking at a grain price which has dropped, as well as fuel price which has dropped. This is based on $5 per bushel as well as $5 gas. and this curve maintains the same shape. You can see a little bit of sensitivity. This max profit started to move a little bit towards more efficient use of the resource, primarily because the value of the commodity or the revenue had come down, so it starts to favor being more efficient with that water, okay? We come up with, looking at a 20% yield reduction due to heat, a max yield, hypothetically, of 214 bushels per acre, requiring 27 inches of irrigation, as opposed to a max profit point, which would now require 24 inches of irrigation. Okay, again, this is something that was hypothetical and is driving this EPIC project. This was the premise by which we entered into this program. Okay, so we come up with some management strategies to try to identify whether this was something that would now be repeatable in real practice. And we looked at was trying to identify high maximum yield producers. Okay, so we're looking at somebody that's got plenty of water, 5.5 gallons per minute per acre or better. And we decided to have side-by-side fields or a split pivot, very large scale, so it was easily identified by producers that this is something that's not just small scale research or isolated plots, but something that's occurring in actual production settings. The legacy was what the control was called, and then the EPIC was what we named our management. We used the producer's current best management practices, including the producer would now select varieties, et cetera, et cetera. And then we would incorporate some technologies. Some of them would be exposed, some of them would be somewhat blind to the producer. The reason for that is so that we can control this legacy plot. When we were entering into this project, interviewing cooperators, many of them said, well, if I start to see that that managed plot's doing better, guess what I'm doing with the rest of my field? And we thought, well, we can't really do that. And it's tough to maintain a control anyway in a production setting, so we really didn't want to have one management that was starting to favor what would be our control. Okay, the technologies we looked at was AquaSpy with capacitance probe, AquaPlanner, which was a crop modeling program, and then Pivot Track, which was now monitoring and control of what the center pivot system were doing. Okay, all of these have been in contact with us today. If you've got questions on them after we go through this presentation, please ask them for their proprietary input on that. Okay, so our protocol, very, very simple goals for 2011. We wanted to, one, maintain or improve grain yield. This was vital because that is the indicator that's currently the standard for I'm a good farmer. Okay, I can yield this grain and I can do it consistently. So what we wanted to show is if we were going to make some changes, we need either to maintain or improve that. The other component of this, which is where this EPIC program really comes into its own, is in the process of doing that, we set out with a goal to reduce irrigation by 1 to 4 inches across that field. Okay? Remember what 2011 looked like, pretty droughty. We didn't have near the opportunities, but I'll show you that our results are still pretty darn impressive in light of that. Our strategy going into this of how we were going to reduce those inches was based off of the total irrigation requirement for a crop that's typically expected. Okay, so we've got a crop. This line here would represent on a, this would be a just a short 5-year average, but the 15-year average is the same. Your irrigation requirement being your ET minus those daily average rainfall events. And what you find is that there's quite a few times during the year where you're actually going to provide on net rainfall some sort of buildup into the soil. You're going to provide water to get to, actually you're going to have a negative irrigation demand on that day is what I'm getting at, because the rainfall is going to provide sufficient water to meet that crop's needs on a day-to-day basis in those cases. What you notice here is that early season corn and late season corn, you've got very little demand for water. You've got some demand because the crop's growing, but you've got to remember early in the season you've got a very small crop. It doesn't have much physiological mass to cool down or to fill with water. And then at the end of the crop, you're working on a natural senescence to get to pre-harvest state. Okay, so neither of those places are really demanding water like you would expect a corn crop, because we typically think of corn as operating at this level straight across the board. Like David Sloan mentioned earlier, this becomes your most valuable water because that's the point where you've got your biggest negative hit usually if you're stressing. And most people don't have capacity to meet up with this anyway. Starting to look at capacity on corn. If you've got 5 gallons per minute per acre, you'll see you'll almost always be very deficit, even in a standard rainfall year from June through mid-August anyway. Okay, start to get into some luxurious water, 6 and 7 gallons per minute per acre, and you start to have some opportunities now to actually manage and meet crop water needs on a day-to-day basis. Our goal with this now was to see going in if we could reduce, say, 1 inch of water here and 1 inch of water here. And if we did get to where we had a fortunate rainfall event that started to spike down middle of the season, we might shut off the irrigation for 1 lap and remove 1 inch or so of water there. That's where we get that concept of 1 to 4 inches, depending on what the season and the crop would allow us to do. Okay, so the reason we decided on that number is we started to look at the volume of this with the water use implications of reducing that 1 inch across the area. In 2010, there was over 900,000 acres of grain corn planted in the Texas North Plains. This comes from the NASS statistics on this. From experience, at least half of those fields are targeting high yield. Okay, it's a guy that's shooting for maximum yield potential. It's a guy with 5.5 gallons per minute or better, some sort of aggressive fertility program, etc. That's just the way we are with grain corn in this area. If we were to look across that at a 1 inch reduction annually on this half of the total acres, so 1 inch over 450,000 acres, we get pretty staggering water savings in a seasonal basis. Okay, and this is where I think this regionally fits in as a very good project. What you find is if you can reduce that 1 inch across this equates to 37,500 acre feet of water across this region, or roughly 12 billion gallons per year of mitigated water use. Now, on the other end, if you can maintain economic sustainability in that, you've now reached that true optimum goal of what we need to be looking at for conservation, especially in production agriculture. Okay, so what did we do to show this in the field? We looked at 5 producers in 5 counties. Basic summaries up there. The counties are Dallam, Sherman County. That Sherman County one is actually right on the Dallam line. We had Hartley, Hutchinson, and Ochiltree counties. All of these in the North Plains Groundwater Conservation District area. The parameters up there, we went from everything from split quarter mile, Lisa pivots to 2 side-by-side subsurface drip irrigation plots. And the goal here was what we wouldn't compare from producer to producer, but we wanted to compare from plot to plot. Now, this in mind, we tried to keep where the plots were as similar as possible. And this, of course, demonstrated that it is impossible to maintain a control and impossible to contain scientific accuracy in the field. It just isn't. Results demonstrations do one thing, and that's demonstrate technology. We cannot prove anything from this just because we don't have enough control over this project to do that. That is certainly one limitation that we have in this, so keep that in mind as we start to look at some of the results.